When you learned how to do products minus reactants, you learned one way of finding the heat of a reaction, the delta H reaction. Another way that it can be done is experimentally. So for example, something like the molar enthalpy of combustion can be determined experimentally by burning something and collecting the heat from the combustion. If we know how much of something we burned and we know how much heat it gave off, we can then figure out how much heat will be released when 1 mole of the substance burns. So here's a sample set of data. Glucose was burned, 0.77 grams of it, and that was used to heat water inside a copper container. So both the copper and the water gained some of the heat. One of the inferences that I have to make from this set of data is that when I'm given the initial temperature of the water and the final temperature of the water, that this gives me both the delta T of the water and of the copper. And that's going to come into play because I'm going to calculate how much heat each one of those things absorbed. Okay. First thing I'm asked to do is to complete and balance the reaction. So glucose is being burned, C6H12O6, and that's told to you here. I don't expect you to know that off the top of your head. Complete combustion is plus O2, forming CO2 and H2O. I have 6 carbons on the left, so I'll need a 6 there. I have 12 hydrogens on the left. A 6 there will give me 12 hydrogens. Now if I add up all of the oxygens on the right, I have 12 plus another 6 for a total of 18. I did not balance this right. For a total of 18, but I already have 6 here, so I only need to get 12 from that. So I'll use a 6, and then I'll balance the oxygens. Okay, now we want to find the total amount of heat absorbed by the water and the copper, which means I want to do Q of the water, and I'm going to add it to Q of the copper. For the water, we had 2,000 grams of it. Water, as we know, has a specific heat capacity of 4.18. The change in temperature of the water went from 19.9 to 34.3. So 34.3 minus 19.9 gives me a change in temperature of 14.4 degrees. For the copper, we have 120 grams of copper. Specific heat capacity of copper is 0.385. And it has the same change in temp of 14.4. So for the water, 120,000 joules, and for the copper, 665 joules. Let me check my math on the first one. Sounds good. Now I'm going to add the two together. Gives me a grand total of 121,000 joules. I'm going to round to 3 sig figs. 2 is probably more appropriate here. Or 121 kilojoules. C is a rather easy question because we're making an assumption here. And that assumption is the conservation of energy. We're assuming that the energy released by the combustion equals the energy absorbed by the water and the copper. So we're going to say this is also 121 kilojoules. Okay, we want to find the molar enthalpy of combustion. Molar enthalpy of combustion is defined as the energy change for 1 mole. So the units that we're looking for is kilojoules over moles. I also want to make sure when it's delta H reaction that I consider whether it's supposed to be positive or negative. So we already know that the kilojoules is 121 kilojoules. To get the moles, I need to use the fact that I know when it was in the data table, that there were 0.77 grams of glucose. Dividing that by the molecular weight of glucose gives me its moles. 0.00428. So now to get the kilojoules per mole, 121 over 0.00428. 28,300 kilojoules per mole. Was this reaction endothermic or exothermic? two ways I can tell. One, it's a combustion reaction, and all combustion reactions release energy. Another is I can tell that the water heated up, so the reaction must have released energy. So that is my delta H for the reaction. The last part of the question here asked me to connect it back to something we did before, which is where we draw an enthalpy level diagram for this reaction. So I'm going to draw my axes. I'm going to label my coordinates, heat, and this is going to be in kilojoules. The X is reaction coordinate or course of reaction. And we're exothermic, so I'm going to start off higher than we finish. I made this a little bigger than normal because I wanted to have room to write in my reactants and my products. So my reactants are C6H12O6 plus 6O2. My products are 6CO2 and 6H2O. And we can show a delta H reaction of negative 28,300 kilojoules per mole. I have one for you to try where you're going to do a similar thing, but for heat of solution. This is a sample problem. It's also on your note sheet. For the dissolving of sodium carbonate, same idea. You want the heat of reaction for 1 mole. It's leading you through the steps as well. The one thing I want you to remember is when you're finding the enthalpy change of the solution, you need to consider the total mass. Give it a try.